Welcome everyone to another webinar today on an introduction to liquid scintillation counting. This is the fourth webinar in the SRP's current programme and is a really important webinar as well because it's the first time we're collaborating with the Association of University Radiation Protection Officers, which is absolutely fantastic to be able to give you a new programme in collaboration. So first things first, in terms of how many attendees have we got? We have an absolutely fantastic number of attendees again today, and we've actually got over 330 people attending. I think we've actually got closer to 340 as we had a few last minute registrations as well. So it's great to see that the webinar programme continues to be a real success, and we want to continue to keep on delivering more and more programmes. So please keep more suggestions coming into us. We've still got other ideas coming in the future, which we'll be shortly announcing, but please keep those suggestions coming in. The usual ground rules apply for this webinar, so questions will be asked at the end of the presentation, but throughout it, please feel free to drop those questions into the Q&A box, which should be available via a kind of speech mark symbol on your screen. The most liked questions will be answered and all others will be answered after the webinar and added to the past event page on the SRP website. The reasoning behind this is just from the previous ones we've held, there normally seem to be far too many questions that come in to answer in the time period. So as I said, if you see someone's raised a question in the actual question box and it's one that you particularly want to see answered, feel free to like it. That will help obviously move it up in the priority list. At the very end of the webinar, please do send us any feedback. So that's including an online survey that will be emailed to you. And that really is helpful for us to determine what we can do to improve this programme going forward. Also, there's been a number of questions over the last few webinars around what you can do to demonstrate you've actually attended the webinar. So if you actually need some kind of confirmation that you've attended a webinar for CPD points, for instance, then please email Charlene to say you've attended and she can drop you some kind of confirmation, but it won't be a certificate, it'll just be more of an email confirmation. We have got more webinars in the programme, a couple coming up very shortly, so please keep an eye out on the SRP website and also the AURPO website. They'll be posted on as well. And we'll be emailing it around the newsletter. But if you have any other further suggestions, please do email the admin team. I also wanted to just hand over to the AURPO president, Professor Peter Cole, which a number of you obviously know as well, to do a bit of an introduction. But I'd just again like to say, thank you to AURPO for co-hosting and collaborating on these new set of webinars. It's fantastic to be doing this as a partnership and really for the good of the profession. And over to you now, Pete.
Thank you, Pete. I hope everybody can hear me. Good afternoon, everyone, and welcome to this training webinar. These unprecedented times of lockdown have had a significant impact on our ability to travel to and attend professional events such as annual conferences and large meetings. This in turn has meant that many of our members may struggle to obtain developmental training and collect CPD points. It gives me great pleasure to say that AURPO are working closely with SRP to deliver a programme of free online training webinars to support the needs of both our memberships. This is a fantastic endeavour and so far has proved to be very successful. So without any further ado, I would like to introduce our today's speakers, who are Dr. Helen Cauldbeck from the University of Liverpool and Dr. Oliver Preedy from Loughborough University. Both are my fellow members of the AURPO Executive Committee. And more importantly for today, I suppose, they are both experts in liquid scintillation counting. And they will be conducting this webinar jointly as a double act. So over to you, Helen, I think.
Hi, thank you for the introduction. And I would also like to say thank you to SRP and AURPO on behalf of both myself and Ollie for this opportunity to present to you today. So we're going to be giving an overview of the basic theory behind liquid scintillation counting, along with some applications of the technique and problems that can occur and how we overcome them. So to begin with, what is a liquid scintillation counter? Well, there is a large variety of liquid scintillation counters on the market that come in all different shapes and sizes, but they all have one thing in common. It is that they're a piece of instrumentation used to determine the level of radioactivity within a liquid sample, predominantly containing low energy beta emitters, such as tritium and C14. Liquid scintillation counting can be used to look at other low energy beta emitters, as well as alpha emitters and occasionally gamma sources, however these are at a reduced efficiency. So today we are going to focus on looking at liquid scintillation counting of low energy beta emitters. So firstly, I'm just going to give a brief overview of the principles behind liquid scintillation counting, and we are going to cover each of these stages in more detail throughout the presentation. But the way scintillation counting works is that a sample is placed within a liquid scintillation vial along with some liquid scintillation cocktail. This is then placed within a liquid scintillation counter. The counter then takes the vial and places it near photomultiplier tubes. So here I'm showing 2 photomultiplier tubes, but the number of these can vary depending on the model of counter that's being used. So the energy from the radioisotope is transferred to a solvent, then scintillant molecule within the cocktail to produce photons of light. These flashes of light are produced isotropically, so the same in all directions, and detected by both photomultiplier tubes simultaneously. The photomultiplier tubes convert the minute flashes of light into measurable electrical pulses. Both photomultiplier tubes then send these electrical pulses to a coincidence unit. If the coincidence unit receives a single pulse from only one side, it's ignored as noise, so this reduces any background levels that liquid scintillation counting sees. If the coincidence unit receives electrical pulses simultaneously from the photomultiplier tubes, it sends a single pulse to the multi-channel analyzer. The multi-channel analyzer then sorts the pulses into channels which relate to energy of radioactive particles being measured. The pulse is then amplified and then counted, and the number of pulses counted is directly proportional to the amount of beta particle energy within the original sample. So the first stage of the liquid scintillation counting process is to mix the sample with liquid scintillation cocktail in a transparent bottle. The beta particle energy is then transferred through the cocktail to produce a flash of light. The normal pathway for this is that the energy from the beta particle decay is transferred to a solvent molecule, shown here as the white dot, and the energy then goes to a scintillant and then finally to an excited scintillant, which releases a photon of light. It is possible that the beta particle might hit a scintillant directly, but solvent molecules are in a greater excess within the cocktail, so this is unlikely. The key message to take from this is that the more energetic the beta particle, the more excited solvent molecules are produced, and the greater number of excited scintillants, and therefore more photons are produced. So the amount of energy from a beta particle is directly proportional to the amount of photons being produced. So there are lots of different cocktails available to optimize the counting conditions of samples. All contain at least one organic solvent and one or more scintillators, and some contain surfactants if the sample being measured is aqueous-based. One important thing to remember and to consider is the waste stream permit restrictions, as some liquid scintillation cocktails can be disposed of via solvent waste, others can be disposed of via aqueous waste streams as well. So as mentioned, the solvent molecule is responsible for absorbing the released energy from radioactive decay. Therefore, the solvent molecule must absorb and transfer energy efficiently. Also, it must not quench the sample. We'll be discussing quenching in more detail in a minute, but basically you don't want to reduce the energy transfer in any way within the cocktail. The solvent must also provide good solubility for scintillators and preferably good solubility for the sample as well. Good solvents are typically alkylated aromatic compounds with large conjugated pi electron systems, as these shown here. So these provide a good target for beta interaction, capturing the energy of nuclear decay. Solvent molecules must also only have a small amount of naturally occurring C14, so you don't interfere with the measurement samples. So solvents can be split into two categories, classic and safer. So classic solvents include toluene, xylene isomers, as well as cumene, but now pseudocumene is used almost exclusively in classical cocktails. So these classical cocktails are highly toxic, so they're hazardous by inhalation, skin absorption, and can be irritating to skin and eyes. They also have a high vapor pressure, so produce a strong smell and must be used within a fume hood. They also have a low flash point from about 5 to 50 degrees, so are highly flammable. So storage within the laboratories must be restricted, and this needs to be thought about before you purchase these classic solvents. Then the safer solvents, and I must stress that these are safer, not safe. These safer solvents include diisopropyl naphthalene and other linear alkyl benzene derivatives. So safer solvents have a low toxicity and haven't had any carcinogenic, mutagenic or teratogenic effects as of yet. They have a low vapor pressure, so don't have the same strong smell as classic solvents. And they also have a high flash point, so above 140 degrees. Another component of the cocktail is a scintillator. These absorb energy released by the solvent and become in an excited state. So on their way back to the ground state, the excess energy is re-emitted at a higher wavelength as a photon. So ideal scintillants have a fast decay time, they have high fluorescence quantum yield, so they are highly efficient in emission of photons relative to the amount of energy absorbed from the solvent. Therefore, they can provide a proportional number of photons relative to the energy of the beta particle being measured. There are two different types of scintillators, primary and secondary. So early photomultiplier tubes weren't sensitive in the region of fluorescence emission of the primary scintillators. For example, PPO, which is the most popular primary scintillator, emits photons at a wavelength of 350 nanometers, and below 400 nanometers, photomultiplier tubes actually lose sensitivity. So therefore, we needed to add a secondary scintillator. So this is also known as a wavelength shifter. So the secondary scintillator is added to re-emit energy at a longer wavelength above 400 nanometers, about 420 nanometers. So secondary scintillators are also electron-rich compounds, which can be excited very easily. So even now with modern photomultiplier tubes, which are generally capable of counting light pulses from the primary scintillator, secondary scintillators have been found to improve efficiency, and in many cases are still included in the majority of liquid scintillation cocktails that you can buy. So finally, in some samples which are not miscible with organic aromatic solvents, a surfactant is used to help form a stable microemulsion. So all radioactive species can be in close contact with the organic solvent for energy transfer. So upon addition of water to a liquid scintillation counting cocktail, large aggregates are formed in which the water molecule is in the middle, and the hydrophilic head of the surfactant interacts with this, while the hydrophobic tail sticks out into the solvent and scintillant molecules. So therefore a stable microemulsion is formed. However, there is the risk of micelle formation in that small pockets of undispersed water won't be able to efficiently interact with the solvent, and the beta particle must get out of the micelle before photons can be formed. This is heavily dependent on the volume of water in sample and the amount of surfactant within the cocktail. So one thing to remember about liquid scintillation counting is that no matter how good the counter is that you are using, a poorly prepared sample can only produce bad or unreliable results. An ideal sample is a clear microemulsion like this one here, which looks just like water. We want to avoid coloured or milky samples or any kind of phase separation on standing. So things to consider are the choice of cocktail, and homogeneity of the sample and cocktail is essential. It is possible to add a secondary solvent to improve solubility. However, you must be careful with the solvent added, as we don't want to quench the sample by interfering with the energy transfer at all. Another aspect to consider for sample preparation is the vial type used. These must be clear and phototransparent. So most common are the use of borosilicate glass as well as high density polyethylene. And thirdly, the sample type must be considered. Ideally, we can add cocktail directly to the sample and no precipitation or separation occurs. As discussed with aqueous samples, we can use a cocktail which contains emulsifiers or surfactants. For buffered solutions, it's best to dilute these, and if the sample's alkaline, we can neutralise it with an acid, but do keep in mind any side reactions which could occur by the addition of an acid. For particulate samples, such as those from scrapings of TLC plates, it's good to use a cocktail which suspends the sample and forms a gel, so it prevents these particulates from sedimenting at the bottom of the vial. And finally, for biological samples, it is possible to use a tissue solubilizer. However, these must be highly purified to prevent interference from reactions which give off light and therefore interfere with the amount of light detected by the photomultiplier tubes. An alternative to using a solubilizer is oxidation of a sample. So oxidation of a sample involves combustion within an oxygen-rich atmosphere. High temperature combustion at approximately 1300 degrees produces carbon dioxide and water. Therefore, this is only suitable to study tritium and C14 labelled samples. Samples containing tritium undergo combustion, and the tritiated water is collected, then counted via the liquid scintillation counter. For samples containing C14 labels, the sample's oxidised and the labelled C14 carbon dioxide is collected and counted. So the advantages of oxidation over tissue solubilizer is that it's a high throughput method, so relatively quick. It can be used to prepare wet, dry or freeze-dried samples, which are relatively large at 1.5 grams. It also has excellent radioactivity recovery, so we don't lose much radioactivity through this process. The disadvantages are the initial expense of purchasing the oxidizer unit, and that it's only suitable for tritium and C14 radioisotopes. The oxidizer also needs a nitrogen and oxygen gas supply to work, and the reagents for oxidation are corrosive and flammable. So now we know how to prepare samples for liquid scintillation counting. I'm going to pass it over to Ollie, who's going to discuss how the liquid scintillation counter works.
So thank you very much for that, Helen. So following on from Helen explaining how to prepare samples and how the beta emissions are converted into sort of light by the liquid scintillation cocktail, I'll now try and go through how we get the photons emitted into something that we can actually count, so how the counter turns it into results that we can actually use. First of all, so the first part will involve the photomultiplier tube, and so Helen has sort of said photomultiplier tube several times, so we should probably explain what one of those is. So that's a picture of a photomultiplier tube that I took out of one of an instrument that we had in the lab that was sort of faulty and no longer used, and so they look like these things. So thank you. So how a photomultiplier tube works. So in brief, a photomultiplier tube converts the produced photons into electrical pulses, and then they can be measured and converted into the results that you would typically get out of a liquid scintillation counter. This starts off by the photons passing through a photocathode, which converts the photons into electrons. There are then a number of electrons, which are referred to as dinodes, inside the photomultiplier tube, and by passing the electron from one to the other, the electrons are then multiplied, so you get more and more electrons as they progress through the photomultiplier tube. So this then is where the sensitivity was why we can detect low activity betas with this, because as Helen's pointed out, they emit very small amounts of light, and so by multiplying that up you can count things and they become more sensitive. And so not only will it allow you to count low energy beta emitters, it'll also let you count low activity samples as well. There is a voltage that is applied to the photomultiplier tube across all of those electrodes, and that allows you to control the amount of multiplied photons. So the graph that is on the right is taken from a manufacturer of photomultiplier tubes, and so you can see that there is the gain on the y-axis against volts, and so what you'll notice is that the gain is increased significantly as you increase the voltage. So the stages depend on how many of the diodes or electrodes that you've got inside the photomultiplier tube, and you can see they have different responses. So which means that you need to make sure that the voltage applied to the photomultiplier tube is very precise, because these are not all linear, and so depending on which section of this needs to be considered, because it will affect the results that come out at the end. So I will sort of summarize that. So there's a sort of cartoon diagram that shows what the inside of a photomultiplier tube looks like. So we can see that there's the light, which Helen explained comes from the liquid scintillation cocktail, and so that will then go through the quartz window of the photomultiplier tube. It will then get focused with the focusing electrons and go past all the diodes and get multiplied up, so that it ends up at the anode at the end. And so then the connections can then pass those electrical pulses to the other electronics in the instrument, so that they can be detected. So I think so. Now we've got those. So now we understand how the photomultiplier tube works. How do we get those electrical pulses into activity determination? So a quick summary is that the low energy beta particle will produce fewer photons, as mentioned by Helen. And so that's because the amount of the activity of the beta particle is directly proportional to the amount of photons produced, and the amount of photons produced are directly proportional to the amount of electrical pulses. Then we can work out what the activity is. So that's explained how the photomultiplier tube works, and so now we should explain what happens with the electrical pulses. Don't know what happened. So activity determination, as we've discussed. So the photomultiplier tube converts the flashes of light into an electrical pulse. So an electrical pulse will look like something like this. So you can imagine that it's a sort of Gaussian peak, and so this one's quite low, but as it's proportional to the energy of the beta particle, the pulse will depend. You can get a range of pulses that are higher and higher. So the higher the pulse height of the so that will be the pulse height is measured in sort of either millivolts or nanoamps, and so the higher sort of the peak of that pulse is, then the higher the energy of the beta particle. So that means that we can work out what the beta particle is. So this low one could be something like tritium. Then so the higher you get up, you get all the way to P32. So that will allow you to produce something called the pulse height spectrum. So if you were to plot the number of pulses against the pulse height, you get a spectrum which might look something like this. So this is obviously been drawn by me, so all the heights of everything are exactly the same, but you can imagine as you move along from the pulse height that there's the higher activity beta particles, and the number of pulses will represent how much is in there. And so this is how the raw data of the counter produces, and that you can use to determine the counting efficiency of the sample of the counter, which we will discuss sort of later on in the presentation. Did I do that, or was that? So However, pulse height is not a particularly useful unit because it will differ from instrument to instrument. So you need to convert it to something that is universal between all instruments and makes more sense to the scientists that are looking at the data. So how can you convert pulse height to EV? So because we know what the pulse height is and we know what the energy of various beta particles are, if we use and the fact that all radioisotopes have characteristic emission values, then you can use some standards and then calibrate your instrument so that you can turn the pulse height which is collected from the instrument into EV, and so that will then allow you to display your spectra that are collected in the form of energy against intensity. So that being said, and so now we've managed to go from having something that is a pulse height spectrum to something that probably looks more familiar to anyone that's done any liquid scintillation counting, but this is a liquid scintillation spectrum of a beta particle. And so the things to note are, so this one here is real data, so it does look a bit bumpy, but it was taken off one of our instruments. So you'll see that we've got the energy in keV against, in this case, normalized activity. And so this is for tritium. So you'll see that it's got, the peak is about a third of the way along the spectrum, and there's a fairly long tail. So that's because beta particles produce a continuum, because when the beta particles produce, the energy is split between the beta particle and the antineutrino. And so a third of the energy is the most common. So if you see something that is a beta particle spectrum, it will look much like this. So we're not really going to touch on counting alphas, but I did want to just put in what an alpha spectrum looks like. So this is some uranium-233. Counting alpha particles, because they are very high energy, the efficiency is very good, nearing 100%. However, you'll notice they are significantly different to the one I showed you previously, where they have a much more Gaussian shape. This is just more for information than anything else, but so you can compare the two. Can you click me on, please? So now I've shown you how the spectrum, what they look like. We should probably explain how they're produced. And so, as Helen pointed out earlier, when they have the coincidence unit. So when two pulses are detected simultaneously, because the flashes are isotropic, the reason that the coincidence unit ignores single is to reduce the background, because the light will be all around. Then because they're produced in various heights, they can be sorted into channels. So and that is done using a multi-channel analyzer, which is just a pulse height sorter. So the greater the energy of the height of the pulse, then the higher number that it will be put into in terms of a channel. So various instruments have different numbers of channels in them. So the sort of tricarb scintillation counters, which I'm sort of used to using, are older instruments, and so they have around about 4,000 channels in them, which corresponds to about half a keV each. So whereas if you look at some of the more modern ones, they will have larger numbers of channels because of the evolution of technology, etc. The more channels that the instrument has, then the higher the resolution of the instrument. So because you have more bins to put your counts into, so you can sort them more discreetly, so therefore you get much sharper images because the resolution's much better. And so again, you use calibration standards to calibrate that for the energy of the particle or the isotope. So you can put it into a channel that is discrete to a certain energy. Oh, too far. So you can imagine that it's important to talk about setting your counting windows. So most of the time when you're setting up something, you'll have to set a window to count between a certain energy certain energy window. So for tritium, it might be between, say, 0 and 18 keV. And so if you're doing research, or if you're lucky enough just to be counting one particular isotope, then you have to make sure that your window is big enough, but theoretically you could count over all of the window, the whole energy range, and you'd encompass everything from that particular emission. However, if you're doing routine like wipe tests or sampling from somewhere, you're probably not fortunate enough to have a single isotope in your in your sample, and so you'll have to think about how you can correct for that. So here we've got an example that will show you the spectrum where we've got 3 that are all overlaid, and so you've got some tritium, some carbon-14 and some P32. So and there's overlap between the 3 of them. But by putting windows in, so for the tritium you could count between 0 and then 18. For the carbon-14 you could go between 18 and 158, etc. Then you can count the majority of the peak and eliminate the interference from the others. However, that won't fully resolve it, because you can see that some of the tail of the tritium goes into the carbon-14, and the same is true. So the way that you would get around that is you can either use software that will help you resolve the peak overlap, which or it will obviously change the counting efficiency, and so therefore you can do some simple maths to account for this overlap. So which brings me nicely on to counting efficiency. So counting efficiency, which is just CE here, is easy to explain in terms of it's the rate that you observe on your counter by what you should observe. So and it's often quoted as a percentage. And so the reason that you should work this out for your instrument is that depending on, it will be different for each instrument, even between the same model, because there are many variables. So you should always calibrate them regularly, and most instruments that you buy, or certainly the older style ones, all will come with a set that you should run through that is shown here, that's got a carbon-14, a tritium, and also a background, so you can check for contamination. So this will show that you'll then turn your counts per minute or counts per second, which is what the machine will show you, into either disintegrations per minute or disintegration per second. So typically for tritium you'll get around just under 60% counting efficiency, and for carbon-14 you'll and higher energy beta particles you'll be nearer 95%. So I think that's it. Now I'm handing back over to Helen. Now I've explained some of the stuff, how the instrument works, so that she can talk through some of the problems that you might run into in terms of quenching.
Thank you. So I did briefly mention quenching before in the presentation and how we want to avoid it, but now I'm going to discuss the different types of quenching possible and how we overcome these. So in general, quenching is a process which interferes in and stops the energy emitted by the radioisotope being caught entirely by the photomultiplier tubes. So there are 3 different types of quenching: physical, chemical and colour. Physical quenching occurs when there is a barrier which impairs contact between the radioactive particle and the scintillator, such as immiscible solutions, or when photons of light are generated are absorbed by some solid within the vial, for example, if the sample is on a filter disc. Chemical quenching occurs when a molecule is present which stops the production of photons. For example, any compound that has a low density of electrons, so it can't re-emit energy as solvent molecules do, or it doesn't re-emit them at the energy, but with a lower efficiency. So prevents energy from the beta particle reaching the scintillator, and therefore a reduced amount of light reaches the photomultiplier tubes. Finally, there is colour quenching, which occurs when the emitted light is absorbed by colour in the sample. The energy transfer occurs correctly, but once the light is emitted by the scintillator, it's absorbed by colour in the sample and doesn't reach the photomultiplier tube. So photons of light are given off in the blue wavelength, as I mentioned before, at about 420 nanometers, and as such, coloured samples which are yellow and red cause the highest level of colour quench, so we want to avoid those. So overall, quenching reduces the counting efficiency, so the increased amount of quenching agent reduces the counting efficiency. You can also see that the energy distribution is shifted to a lower energy. So here we have an unquenched C14 sample. As we add a chemical quencher of carbon tetrachloride, you see that energy distribution shift to the lower energy range. So there are various ways to correct for quenching. One method is to use an internal standard, such as these photographed here. A sample is counted, then a known amount of radioactivity is added from these standards to your sample, which causes a predictable increase in DPM. So the difference between the measured and the observed DPM from this sample is then due to the quenching. And therefore we can calculate the counting efficiency and calculate the activity in the original sample from this. This method is quite time consuming, however, as each sample must be counted twice, and it is destructive to the sample as you need to add that additional radioactivity. Other methods to correct for quenching involve the generation of quench curves. So a series of standards as shown here, in which the DPM is constant and the amount of quenching increases can be used. The quench indication parameter CIS, or spectral index of the sample, is derived from the sample spectral endpoint. And as I already mentioned and shown here, with increasing quench, the average kinetic energy of the beta particle decreases. So the accounting efficiency is then determined for the series and plotted against this CIS parameter. Samples with unknown quench can then be measured and the value of CIS given by the counter. You can then work out the accounting efficiency of the sample. So here, for example, say we have a CIS value of 12 with a CPM of 10,000. From the curve, we can determine the counting efficiency of 56%. The DPM can then be calculated by dividing the CPM by the counting efficiency to give the actual amount of radioactivity in the sample. However, this quench curve technique isn't good for low activity samples, as CIS may not be accurate, and therefore the calculation it can't be either. This method also can't be used for samples containing a mixture of isotopes. Finally, an external standard within the liquid scintillation counter can be used to generate a quench curve. So some liquid scintillation counters come with a built-in gamma source. After the sample is counted, the liquid scintillation counter automatically places the sample next to the gamma source, which provokes the ejection of Compton electrons from the atom in its environment, which are very similar to beta particles and will induce the same scintillation effects as beta particles do. So the transformed spectral index of the external standard, or TSIE, is determined of the external source, then the quench of an unknown sample can be determined. So similar to the previous quench curve method, TSIE is used to determine counting efficiency and the true radioactivity within the sample. The method is advantageous as it's non-destructive to the sample. It's automatic by the liquid scintillation counter once set up, so it's very quick. And it provides simultaneous colour measurements of the sample and works for low activity samples as well as samples containing a mixture of isotopes. So now we know the theory behind liquid scintillation counter, I'll hand over to Ollie to discuss decommissioning and some applications of liquid scintillation counter.
Thank you very much again, Helen. So here's a picture of a liquid scintillation counter. So this, you can see, it's an old sort of tricarb 1900 TR. And so for we needed to sort of get rid of the instrument, and so because it was faulty and no longer working. So there are many things that you need to consider about when you're getting rid of a liquid scintillation counter. So such as this one weighs getting on for 250 kilos because there's a lot of lead shielding in the back. As Helen mentioned, it's also got a gamma source in it, a barium-133 source. So it's not, although it's an electrical item, it can't go straight away as we. And so if you wanted to deal with it, it would need to go by a specialist waste contractor. But luckily, we had the expertise in house to be able to sort of deal with it and remove the source. So I will. Obviously, all scintillation counters will be different, but this is just sort of a summary of the approach that we've taken on this one. So if you take the panels off the front of and the sides of the liquid scintillation counter, you'll see a lot of wires and other bits and pieces of electronics. So again, you should be careful because the voltages that this operates at are quite high, and so you should make sure that you've isolated it from the power before you do anything like this. So hopefully, so you can probably just about work out here where my mouse is that there's something that looks like a the round cylinder, which this is actually the mechanism that inserts and retracts the barium-133 source. And so it's on the end of a spring, and so you can remove that to get the source out. So after we'd removed the source already, but this is just a close-up of what the mechanism looks like. So as we managed to remove the whole thing. So you can see there's a motor, and you can make out there's a chain-driven piece here. The spring goes up and down this pipe, and actually you can see this is the mechanism that is slid backwards and forwards. And here's this spring. So what we did was we cut the end of the spring off, so we left quite a bit on so we weren't getting anywhere near the source. So this sort of very blurry bit of metal that's at the end, which is very, very small, is the barium-133 source, which is the internal standard of the liquid scintillation counter. So we can then dispose of that using our sort of via the normal waste routes that we have available to us in accordance with our permits, etc. And we can move on. And then once the radioactivity is removed, we also removed the lead as well, which is a fairly tricky job, but we also have got rid of the counters just by removing the source via normal weed collection. So this kind of brings us on to applications of liquid scintillation counting. So one of the processes that we're currently going through is there's some decommissioning of one of the facilities that we have. And this is going to be discussed further in an upcoming SRP AURPO webinar, which I'm not entirely sure if that's been announced yet, but it's certainly, I'm guessing, is coming soon. And so we'll talk about how one of the things that we need to do is wipe tests to demonstrate that the areas are free from contamination. And because tritium and carbon-14 were used, along with some other low energy betas, we needed to do wipe testing of everywhere. So we'll go through how to convert from counts per minute to becquerels per centimetre squared. Oh, God. So when you're doing any sort of wipe testing, you need to sort of make sure that you have a process that's agreeable with you, and you might also have to consult the Environment Agency to check that they're happy with the method that you're using. But you can also consult British standards and those sort of things. You need to work out what sort of area to be surveyed. So if we're doing typical swabs around the lab to check for contamination when it was in use, we would use a 10 by 10 centimetre square area, and we do those routinely. So you'd have 100 square centimetres. But if in this case you can see that the grids which have been put on the walls are much sort of bigger, so because of the area that we needed to survey. And then there you need to consider in your calculations the efficiency that you think of removing the material. So we nominally use sort of the 10% value, which is probably fairly conservative, as there's been research done into this which would show that the removal of depending on different radioactive contaminants from different surfaces is incredibly low, sort of below 1%. So we use a 10% so that we're being conservative. And then you need to consider the counting efficiency of the instrument as well. So when you're doing a wipe test, so you need to take a swab first of all. So we use a damp swab method. So you can either use things like filter paper, sort of cotton buds, or Q-tips are quite good as well. Yeah, you can use things like tissue, so Kim wipes are quite good, or you can buy special wipes for doing wipe tests which dissolve in the scintillation cocktail. But there's all manner of things that you can use, including using things like packing peanuts. So it's there's a whole load of things that you can use. The important thing to make sure that when you're doing this is that whichever method you choose, you should use a background and do some testing beforehand so that you can demonstrate that you're not getting any other interference. In terms of solution, we either use 10% acetone or 10% ethanol, so as that does a fairly good job at removing it. So you then prepare your sample as outlined by Helen, and then you put the sample in and you count it, and you'll get some numbers out of the liquid scintillation counter. Although not that one, as you saw earlier, it has been decommissioned. So how do you get from the counts that come out of the machine to a value that you can report against? So you have your swabs, and so you'll get a value. You need to divide it by the sort of the counting efficiency. So in terms of the counting efficiency, you will need to determine that sort of yourself, but or use a value that you think is conservative. So we could use a value that's say 50%, etc. So which is fairly low. And that'll give you an activity that is in the activity that's in the vial from your swab. However, you then need to consider how effective what's actually been removed and what's left on the surface. So if you take the activity that you've got from the vial and you divide it by the efficiency that you've determined, so this could be 10%, that will give you an activity in becquerels that is in your surveyed area. So then when you know what your activity is and you know what the area is that you surveyed, if you divide one number by the other, then that will give you the activity in centimeters squared or meters squared, or the area that you surveyed. And so you can say that there are 10 becks per centimeter squared, etc. in this square over here. And so I think that is that's me talking about wipe testing. So I'm now going to pass you back over to Helen, who will explain how she does some of she uses liquid scintillation counting in her research.
Thanks, Ollie. So in a university setting, liquid scintillation counting has been invaluable, a technique for my research, as it provides a level of accuracy not possible by any other methods. So the way that I use liquid scintillation counting can be split up into these 4 different sections. So synthesis, determining formulation and release, deposition and permeation of radioisotopes through materials, and finally hyphenated techniques. So monitoring synthesis by liquid scintillation counting can be used to determine rates of conversion of reactions and reaction mechanisms by tracking the radioisotope during the reaction. Similarly, we can track radiolabeled compounds during formulation of various materials. We can then monitor how the radioisotope is released from these materials. So for example, here we generated a number of different polymeric nanoparticles containing a radiolabeled drug. We then used dialysis and took liquid scintillation counting measurements of the reservoir to monitor the release of the drug from the nanoparticles. So this graph shows how we got the different rates of release depending on the polymeric material used within this experiment. We also look at deposition and permeation of radioisotopes through various materials. For example, we can use a Franz cell setup like this, where we place a membrane material such as porcine skin over a reservoir solvent. We would then place a radioisotope on the top of the membrane in this donor chamber here, and take samples of the reservoir underneath at set time periods for liquid scintillation counting. So here are some results from using this method, where a topical dose has been applied to the skin and an intradermal injection administered. And as you can see, there is a fast release into the reservoir of the sample injected, and there is no release from the topical dose. At the end of this experiment, we can then section the skin into thin layers and oxidize these thin layers to determine and count those samples to determine the deposition of dose within the skin. So as you can see here, from the topical dose, we get a lot of radioactivity on the surface of the skin, and there is still some in the lower skin layers. This technique also provided that when you've got the intradermal injection, it bypasses the top layers of skin, but there's still some in the lower layers of that skin there. So finally, we can hyphenate traditional analytical techniques with liquid scintillation counting to provide another dimension of analysis. For example, gel permeation chromatography to analyse polymers, or thin layer chromatography to look at smaller organic molecules. And we can use these to track exactly where on a material the radioisotope label is and how radiopure the material is. So now we know what we can use liquid scintillation for. We're going to discuss some of the common problems that you might find with liquid scintillation counting. So if your counts are too high, this may be due to photoluminescence. So UV light causes photon emissions, which can interfere with your counts. And these will decay quickly. So the best way around this is to leave your sample in the dark for a while before counting. And this is known as dark adapt. So for example, seaweed requires to be stored in the dark for many hours to reduce counts from millions of DPMs to thousands. And if you do measure a sample that is photoluminescent, you'll see quite an erratic series of results. Counts can also be too high due to static electricity, which can be present on the surface of the scintillation vial. So one way around this is to use a static eliminator, or alternatively, you can simply run water over the vial. And finally, counts could be too high due to chemiluminescence, which is the emission of light caused by a chemical reaction. So ideally, to remove chemiluminescence, you'll just wait for the reaction to terminate before counting. Alternatively, you can count repeatedly until the sample gains stable results. And the reactions causing chemiluminescence can also be sped up by heating the solution, but you do have to be aware of any additional safety concerns from doing this, and the sample does need to be cooled before counting as well. So alternatively, the samples you're counting could be given counts which are too low. As we discussed, this could be caused by quenching, and we've talked about how we can correct for this. Low counts could also be caused by optical interference, for example, not using a photon transparent vial or labelling the vial incorrectly, so on the sides and not on the lid. We've also discussed the importance of correct sample preparation. So if the sample isn't soluble within the liquid scintillation cocktail, this will reduce the counts. For liquid samples, this can be overcome by the addition of a solubilizer, but you need to make sure that this doesn't quench your sample. And increased mixing, such as sonicating samples, can also help. If the sample is a solid, they can be homogenized, macerated, a solubilizer added, or alternatively oxidized. We've also talked about samples which are particulates, where we suspend them in a cocktail which forms a gel, so it prevents these particulates from sedimenting at the bottom. And as well, you can have samples which are on solid support, such as those on filters. And for these, just allow time and well mix the solution to overcome this. So finally, I'm going to pass back over to Ollie to cover some mechanical problems of liquid scintillation counting.
Okay, so some of the things that can go wrong. If you're using one of the older scintillation counters, so like the tricarbs that we've seen in some of the pictures, they will come with paper that is on a dot matrix printer, and there's no internal memory, so you can leave a whole load of samples that are running in the auto sampler, leave them running overnight after you've allowed them to dark adapt, and then come back in the morning and you'll see a big stream of paper where it's all been chewed up and you've lost all your data and you have to recount them. So one way that you can get around that is you can count them on floppy disks, but that's not necessarily always the easiest way to use them. And then I'm surprised they still make them, but you can still get them on Amazon, etc. This obviously isn't a problem with newer systems, but not everyone has the sort of the fancy new systems and might be trying to make do with something that's a bit more low tech. So heat is a problem. So most electrical components and things like photomultiplier tubes, if they get too hot, so the summer that we had last year where it was getting up to sort of mid 30 degrees or so in the labs, etc., some of our scintillation counters just stopped working. So where they stopped sort of displaying any values whatsoever. So one way that you can get around that is you can buy these sort of chilling condenser units that fit on the back of the instruments. And so they have their own set of problems, as you can come in and find that there's a puddle of water over the floor, which is in a lab that deals with radiation is always a worry. And you have to sort that out because obviously then it isn't cooling the instrument properly. So waste boxes. So depending on the waste stream that you have for your scintillation waste, then they'll go in little the scintillation vials, and they might be picked up for incineration. So obviously you're dealing with a liquid which has got potentially or does have radioactivity in it. So you need to make sure that the lids are fastened, because obviously there has the potential to go everywhere and be knocked over and cause a spill. And finally, you need to think about what you're going to do with them when you finish. So there's decommissioning the liquid scintillation counters. They sometimes go wrong. They need regular servicing, etc., because there's a whole manner of problems that can go wrong. So they need to be looked after. And when you're wanting to get rid of them, because of the shielding that's in some of the instruments, they are incredibly heavy, and so will require all the appropriate means of moving them around and being collected, etc. So I think that, so we have a few useful resources that there are links here. So they're British standards that you can use for testing things like water quality. The PerkinElmer website has got an awful lot of really good information. And there's also the National Diagnostics Principles and Applications of Liquid Scintillation Counting. It's a really good resource. So I think that brings us to the end of the presentation. So all it leaves for me to do from both me and Helen is to thank you very much for listening to our presentation.